Hey guys, sorry I'm not at school today. I actually woke up like really sick and yeah, it wasn't pretty. But I took a bunch of medicine and I'm gonna try to like muster up my energy to get this out for you because I want you to be able to do something today in class. Okay, so this is the last video for our periodic table and periodic trends unit. And it's going to be really quick, okay? So the only thing we have to go over is the reactivity of the alkali metals and halogens, and then the exceptions to the trends in ionization energy. So you guys already know that alkali metals are very reactive, specifically with water, which is why if you put a piece of an alkali metal in water, it will explode. But that has to do with the fact that they only have one valence electron, so they're extremely reactive. So the general equation for the reaction of alkali metals in water is if you have M standing for the metal, and then you have water here, it forms metal ions and hydroxide ions, and as well as hydrogen gas. So you notice that the alkali metal is going to be solid form, water is liquid, then hydrogen is obviously the gas, and then the M plus just represents whatever the metal is, like for example sodium, potassium, magnesium, whatever. This is they're going to be in their ionic form, because whenever the metal reacts with water, it ionizes them, and so that's now going to be aqueous because ions are soluble. And then there's going to be some hydroxide ions in solution as well, because it literally like splits off the hydrogen from water. And that's why there's so much like heat release, because there's a lot of energy that happens whenever the hydrogen is removed from the water. So here's an example. We have a reaction of potassium metal and water to produce hydrogen gas, potassium ions, and hydroxide ions. The charge will only be +1 for alkali metals, group 1 metals. If this is happening with a group 2 metal, an alkaline earth metal, which it still can, then it's going to be a 2+ charge instead of a 1+ charge here. So just like alkali metals can also react with water, they're also extremely reactive with halogens. They react usually very violently, producing a lot of heat in the process. And that's because, of course, just like the alkali metals want to lose their valence electron, the halogens want to gain. So if they come in contact with a halogen, they are going to react to form a salt. So, for example, lithium and chlorine gas, and notice the halogens are diatomic, so make sure you do that appropriately in the equation. Produces lithium chloride, which is a salt here. Make sure the equation is balanced. So anytime you have any alkali metal in a halogen, it's just going to produce that resulting salt. So speaking of the halogens, they have a trend in their physical properties going down the group. So for example, going from fluorine, chlorine, bromine to iodine, it goes from a gas to a liquid to a solid. And that's because the size of the atom gets much larger as you go down the group. So there's more electrons and there is more movement of those electrons in the atom. And so that creates instantaneous dipoles, where at one point the atom might be more positively charged on one side and negatively charged on the other, which causes temporary attractions between those dipoles, and therefore the intermolecular forces will be stronger the bigger the atom is. And so what I just described to you was London dispersion forces, which we talked about last year, but I thought I would review it for you. So as you go down the halogens, because the London dispersion forces get larger, they get more likely to be solid at room temperature, which is what we see. Fluorine is a gas, chlorine is a gas, bromine is a liquid, and then iodine is a solid. Also notice how the density gets larger going down the group, and that's for the same reasons. And also the colors change. So go from yellow to yellow-green to reddish-brown to violet-black, which is an interesting physical property change as you go down the halogens group. And this is actually really interesting as to why the color changes. So obviously, as the atom gets bigger, the difference in the energy levels gets smaller. We learned that when we were talking about the spacing between energy levels. They get closer together as you get farther from the nucleus. And so because of that, when you get like to iodine, the electrons have smaller energy to jump whenever, they are excited by light, or even if they're just in regular white light. So when those electrons move and then fall back down, because it's smaller in energy, it's resulting in longer wavelengths, which is why we see darker colors. So because the gap in the energy levels is smaller, like when you get to iodine, so when the electrons move to higher energy levels, like when they absorb light, like white light or, just regular normal light, the reason that we see purple is because when the electrons are excited and bump up, they absorb lower energy or longer wavelengths light, and so we see the complementary color of what is absorbed. We have learned that, especially, when we're talking about transition metals. So it's also true with the halogens. We will see complementary to what light is absorbed by the compound, and so we're going to see purple, which are shorter wavelengths, but that's because longer wavelengths are absorbed by the atoms. Okay, so if you are in AHL, which stands for additional higher level, there's a couple things that you guys need to know about ionization energy and breaking of the trends. Even if you are going to choose the SL route, this is important information to know, and I really don't differentiate in junior year between HL and SL, so just everyone learns it. Okay, so we all know ionization energy generally increases from left to right because the nuclear charge increases and the number of energy levels stays the same in a row, right? So when the nuclear charge increases, that's going to take more energy to remove the valence electron, resulting in increased ionization energy. So it also decreases down a group, and that's because there are more energy levels as you move down a group. So even though the atomic number is going up, there is more shielding going on. And so it's actually going to be a little bit easier to remove the outermost electrons going down a group, although a lot of things don't exactly follow this. It's kind of very a minimal increase in ionization energy. Then there are discontinuities in the trend going across a group, going from left to right. These give evidence for the existence of energy levels as well as for sublevels in the atom, and we're going to talk about that. So you can see here, going from left to right, generally the trend is increasing, right? But you see this break here, especially between beryllium and boron, between nitrogen and oxygen. You see a break between magnesium and aluminum, phosphorus and sulfur, and we're going to go over that in a second. So let's look at aluminum first. We're going to look at a graph of the logarithmic ionization energy, the logarithm of it, so that we can get like a bigger vantage point of the differences in ionization energies. If it was just the regular ionization energy, then that graph would be like a lot steeper and more difficult to see what's going on here. But so this is the ionization number, which just means the number of electrons removed. And you can see because aluminum has 13 electrons, there are 13 ionization numbers because it can remove 13 electrons. The first three are very easy to remove because they're in the valence shell, so it takes the least amount of energy to remove them. But then you see this significant jump from the third to fourth ionization number, and that's because as you move from this electron, the third, to the fourth one is now in the second energy level rather than the third. So it's closer to the nucleus and it's going to take more energy to remove. So all of these 8 electrons represents the electrons in the second energy level. And then you see a jump once more going to the third energy level because these are the closest to the nucleus and they're the most difficult to remove. So this graph don't use the word prove. I'm sick. Please forgive me. This graph supports the existence of energy levels in atoms. But now let's look at a different graph. Instead of the log ionization energy, it's just regular ionization energy. And that's because we want to kind of see in closer to that trend in a specific energy level. So again, we're looking at aluminum, and we're going to start here with the fourth ionization number. So these are representing the electrons being removed from the second energy level, and you can see that this represents the 2p sublevel because they're removed from the p sublevel before the s sublevel in the second energy level. And there is a jump here between the electron removed from the 2p subshell and then the electron removed from the 2s subshell, so between the 9th and the 10th ionization numbers. So the reason for this jump is because the 2s subshell is actually a little bit closer to the nucleus than 2p. And you might be thinking, like, that doesn't make sense. They're both in the second energy level. But remember, the shapes of these sublevels are different. The s sublevel is more spherical and the p sublevel is more dumbbell shaped. So generally speaking, the s sublevel is closer to the nucleus than the p. Okay, and then I think this is the last thing we have to go over, yeah. Okay, so let's look at exactly how these electrons are removed from aluminum one by one. So the first electron is going to be removed from the 3p orbital in aluminum because it has one electron in the 3p, so that would represent the first ionization energy. The second and the third ionization energy represent the removal of electrons from the 3s sublevel. And then after the first 3 electrons are removed, we get to the 4th, 5th, and 6th ionization energy, which represents removal of electrons from the 2p sublevel. However, you can see that they are removing one electron from each orbital. They don't remove both electrons from one orbital and then move to the second. And that is again because of Hund's rule, how electrons prefer to be single before being paired up. And so they're going to remove in the same way they are added. So you can see here it's moving. This is the 4th, 5th, 6th ionization energy, then 7th, 8th, and 9th. However, in the 4th, 5th, and 6th ionization energy, they have to remove this electron from an orbital that's full. So these electrons are paired. And so because of electron-electron repulsion in these paired orbitals, it's actually going to take a little bit less energy to remove the electron from the 4th ionization energy, the 5th ionization energy, and the 6th ionization energy. It's going to take a little bit less than the removal of the 7th, 8th, and 9th. And that's because, again, once you remove those electrons, then the electrons are so low, there's no electron-electron repulsion going on anymore. So these are going to be a little bit higher, which again supports that trend of increasing ionization energies with ionization number, right? So because of that, when we're looking at the graph for, aluminum and how the ionization energy changes with ionization number, increasing ionization number across the second energy level, you see a steady increase in the ionization energy. And that is because of this nuance here where it takes less energy to remove a paired electron than a solo electron. Okay, and here is some important vocabulary that we have already discussed this unit, but I just put it here in case you needed a refresher on that. All right, guys, that's everything for this video. I hope you have a good day. Work will be loaded in Canvas. Please take a look at that. All right, bye.